Okay, so perhaps it's time to start. Let me just check a final time if I can still be heard. That still works. Okay, great. So welcome everybody to our online seminar. Tonight we are celebrating the winners of this year's Paul Ehrenfest Best Paper Award for Quantum Foundations. Now, needless to say, it would be much more fun to have this in person, obviously, to meet for a few snacks and drinks after the talk like we had in the years before. Now, unfortunately, this is impossible because of the pandemic. I hope you will nevertheless enjoy this evening, and perhaps the question and answer session that we will have after the talk can be an opportunity to meet up and to have some discussions in a similar way as you would have during a regular seminar. Now, what is the Paul Ehrenfest Best Paper Award for Quantum Foundations? So this is an award that's organized by the Institute for Quantum Optics and Quantum Information in Vienna. And the aim of the award is to raise awareness for the field of quantum foundations and also to draw attention to new and interesting achievements in the area without delay. So it's awarded annually for the most significant publication in the foundations of quantum physics. And for this prize, we take into account papers that have been published in the last 5 years before the call. The winner is selected by an international committee. This year, the committee has consisted of Chris Fuchs, Benjamin Huar, Cindy Regal, Valerius Carani, and then myself, Markus Müller. So let me first say thank you to my fellow committee members for the hard work. So I've seen at least Benjamin here, perhaps some more. So thanks again for doing this. It was hard work because we received a large number of submissions. So it was a tough decision. But we are very happy to award the prize to a really groundbreaking experimental result. So this year's Paul Ehrenfest Best Paper Award goes to Peter Asenbaum, Chris Overstreet, Tim Kovaci, Daniel Brown, Jason Hogan, and Mark Kasevich for the publication Phase Shift in an Atom Interferometer due to space-time curvature across its wave function. And we have awarded the prize for the measurement of gravitational tidal forces in an atom interferometer, thereby establishing a new telescope into the foundations of quantum theory and gravity. So let me congratulate all the prize winners. I cannot really shake hands now, unfortunately. So I thought we'd do this symbolically. I have a certificate here, so certainly every one of you will get one of those by mail afterwards. And perhaps whoever is here among the winners can just show up and show the video for a bit so that we can take a screenshot. And please now feel your hands shaken. And again, congratulations very much from all of us on behalf of the committee. Okay, maybe once more. Not sure if Benjamin already did a screenshot. You did? Okay, thank you. So congratulations. Now, let me introduce today's speaker, and one of the winners of this award is Peter Asenbaum. So I was really happy to find that Peter Asenbaum is basically a local. So he studied physics in Vienna at the University of Vienna. He received his master degree in physics in Vienna in 2009 and his PhD in 2014, also at the University of Vienna in the group of Markus Arndt, with a thesis on cavity cooling of silicon nanoparticles in high vacuum. Then from 2014 until 2019, he has been a postdoctoral researcher, and since 2019, a research scientist working on atom interferometry in the group of Mark Kasevich at Stanford University. So one final comment. If you have any questions, then please save your questions until the end of the talk. We will have a question and answer session of at least 15 minutes, maybe later if you like. So this will be an opportunity for all of you to ask your questions, and I actually hope that we'll use this opportunity so that we can have some nice discussions afterwards. Okay, now without further ado, let's start with the talk. So Peter, the stage is all yours.
Okay, so hello. First of all, of course, thanks a lot for giving us this prize. I think we're all very happy to receive a prize for quantum foundations. Let me share screen. Okay. So first of all, it's nice to get a prize for quantum foundations, because you work every day in the lab really hard, kind of to solve technical issues and problems specific to your system. And if you do everything well, you kind of get rewarded for contributing something to fundamental physics. So it's a great reward to get a prize for that too. Okay, so I was a little worried that my voice will be not in good shape today, but yesterday was a surprisingly relaxing day, so it's all good. Yes, as you can see, here's our paper title, Phase Shift in an Atom Interferometer due to Space-Time Curvature across its wave function. So it sounds a little difficult, but actually the whole experiment in the paper can be described in one sentence, namely gravity stretches quantum state. So a few years ago when the paper was published, somebody who was writing a blog article about the paper came up with this sentence, which I find to be very concise and describes the experiment really well. So what quantum states do we have? So we work with cold atoms and atom interferometers. So what is an atom interferometer? Basically, it's an atom cloud or single atoms that are split into two paths and that are separated by some distance. So typically in our experiments, those are really like macroscopic states, and the atoms are delocalized over tens of centimeters, which is an important feature for the described experiment. So how does the experiment work? We just have some atoms in this large quantum state, and then we just look what happens if we bring some source mass. In our case, it was a few lead bricks. We bring them close to the atoms and see what you might ask yourself, why is this interesting? Why do you try to look for gravity? Like a really trivial experiment, why not just do it with electromagnetic interactions or some easier way? So the first thing you can say is, why do it with gravity? There are not so many fundamental interactions. On the one side, you have quantum fields, which are very well described or predicted by quantum field theories, strong interaction, weak interaction, and electromagnetic interaction.
Excuse me, Peter, there's a problem with your microphone and sometimes the sound goes. I think it's when you move, maybe, I don't know, something switches or something, but sometimes I cannot hear you.
Okay. So,
yeah, like that is fine.
Okay, I will come a little bit closer. Okay, so there are not so many fundamental interactions. So one could say, why not just test all of them, what they're doing? Kind of test their quantumness. So the quantumness of the quantum fields, the strong, the weak, and the electromagnetic interactions are very well known. So basically, this is what we call quantum, how those interactions behave. And kind of what this experiment is all about is to do kind of a baby step and try to figure out how quantum gravity is. So we want to learn something about the quantumness of gravity. So this is the main motivation. And in principle, we don't know so much about this aspect of gravity yet. Yeah. So how are electromagnetic interactions mostly? Since I'm working in a low energy lab, all we really care about are the dynamics of the electromagnetic interactions. So how are they different from gravity? So first of all, you can say, oh, electromagnetic interactions are a lot stronger. So gravity is very weak. So you might wonder, does this change anything about the
So, Peter, sorry to interrupt. There's again
Yeah.
a problem with your sound. It seems like when you go further away from the screen that you get muted automatically. So if you can just be a bit closer to your laptop, I think.
I'll try to stay close. Sorry. Okay. So at first sight, a big difference between electromagnetic interactions and gravity is that they are. So on the other hand, they might seem very similar. So if you look at point particles and their interaction, you will see that that the acceleration, for instance, between charged particles, charged monopoles, and the acceleration between a massive object scales as 1 over the distance squared. So in this regard, they kind of feel very similar. So you could expect the quantumness of gravity to be very similar to the electromagnetic field or electromagnetic interactions. But then again, if you look a little closer, you might wonder, what is there? If you look in a certain local region around our little positive test particle at the top and our massive test particle at the bottom, so what means a local region? Local region just means it's a small spatial region around the test particle. So it's in principle, it's much smaller than the distance to the highly charged particle or to the massive particle down here for gravity. So the size of this local region also depends on your sensitivity. The more sensitive your experiment is, the smaller this region kind of is. Or that the smaller the region is that remains local. So in the case of electromagnetic interactions, what you can do is you can stay in this local region and just add different test particles. Oh yeah, first of all, what happens to this positive test particle? It will accelerate towards the negatively charged particle over here. So you can stay in the local region with electromagnetic interaction and just add different kinds of test particles. For instance, you could add a negatively charged particle. This negatively charged particle obviously will accelerate in the different direction. So there will be lots of dynamics going on inside this local region. Especially the two particles will accelerate away from each other independent of their, if you assume that the interaction between them is small. So you cannot only add like different charged particles, but you can also add neutral particles. And obviously they will not accelerate a whole lot, or at least a lot less than the monopoly charged particles. What you can say is that due to this big charged particle on the right, there is a certain observable field in this local region, because you can see the effects by just choosing your test particles and doing experiments locally. So on the other hand, what about gravity? So you can add to this local region, you can add now a different particle. But as it turns out, for small particles, in comparison to the big particle on the right, those two particles in the local region will accelerate the exactly same way. And inside this local region, you will see no dynamics at all. Nothing will happen. And this is true basically for every test particle you can think of. It is true for every test particle you can think of. There will be no dynamics between them, with the only assumption that they are small, or small mass. What you can say is that inside the local region, in the case of gravity, there is no observable field. There's just nothing there. This is just a way of framing the equivalence principle. Locally, you cannot observe gravity. You will not know whether the Earth is there or not. You just stay inside this local region. So from this perspective, the two look very different. And this is also the reason why gravity is so well described by geometric theories. So if you think about geometry, it's very obvious that if you sit on the geometry, you will not learn anything about the geometry by just staying locally or just staying close by. However, if you wander out and try to explore the geometry, you will learn something about it. And this is exactly how gravity works. So you cannot just stay local, but you have to move out a little bit and compare test particles that are displaced by, that are outside this local region.
So Peter, sorry,
Yeah.
Final interruption, final attempt. You're still sometimes lost for the sound. There have now been in the chats a proposal that maybe you can go into your settings and you deactivate the noise suppression, because it seems like Zoom just cuts off your sound when you get below a certain noise, certain level or so. So when you look at the chat, the last two entries gave a kind of a hint of what you could try. Maybe we can try this, and if it's not better, then let's just go on like that, because it's okay. But sometimes we lose you, and it would be a pity to overhear what you're saying.
Maybe automatically adjust volume.
Yeah, the gesture was here to disable that.
So can you hear me now?
So far, it's as before.
No, so
there's a noise suppression somewhere in the audio properties. It can be high or low, or so. I think it can even be deactivated. So perhaps trying to deactivate noise suppression. I'm not an expert on Zoom at all, so I'm just here relying on some tips from the audience. Yeah.
Yeah, don't find the noise suppression. I disabled the automatically adjust volume.
Okay, I mean, maybe let's try that. And we heard you most
of the extended menu.
So that's okay.
Advanced. Oh. Echo cancellation. Okay, I'll turn all of them off.
Okay. So can you still say something test-wise?
Okay.
Yeah.
Let's go back further. Is that still okay?
Yeah, I think so. So let's just try. And if it's not perfect, then it's okay. I will not interrupt you any further unless you're completely out or so. Okay.
No, I mean, it's fine.
Now here you will. So let's try again.
Yeah, talks are supposed to be interrupted. I feel like.
Yes, I think. Ah, yeah. Okay, there you go.
So I will quickly summarize this slide if I haven't been clear so far. In the local region, for the electromagnetic field, you will observe the field just fine. In gravity, you will not observe anything because every particle will accelerate the same way towards the Earth. There will be no dynamics in the local region. This is why geometric theories work so well, like general relativity, to describe gravity. And in these theories, gravity is represented by the curvature of space-time. Okay. One nice illustration of the differences between electromagnetic interactions and gravity are the dynamics of the field. So for electromagnetic fields, we obviously know we have electromagnetic waves, and we have dipole radiation. For gravitational waves, though, there is no dipole radiation. It's not allowed, and only quadrupole radiation. Okay, so what can you learn about how quantum gravity is? You can start with just comparing your quantum states to classical objects, basically in a local environment. the very first and very famous experiment done with a neutron interferometer did just that. They did a pretty microscopic neutron interferometer and measured the acceleration towards the Earth and compared it with a classical particle, and it was basically the same. The interferometer was still small, so it was still kind of a local experiment. And initially, there was actually some controversy about this experiment because the result was presented in this somewhat complicated way. And as you can see, that this phase shift, there appear certain parameters that seem to be in conflict with the occurrence principle. So there's the mass of the particle showing up, the wavelength. But if you account for all the dependencies, you will figure out that the experimental results did not depend on any properties of the neutron whatsoever. So this experiment kind of was the first, or at least the most famous, equivalence principle test with a quantum system. So we did a similar experiment with a little bit higher precision recently by just taking different atomic species and made again a local experiment, tried to keep them very close together and looked for some observable accelerations. And we can find them, not surprisingly. Okay, so what can you do next? So you can use quantum systems to kind of measure gravitational effects in a classical way. So in the beginning of 2000, there was the first implementation of a gravity gradiometer, which simply means that you have two displaced quantum systems and you measure their relative acceleration. So as you can see, both of the interferometers are accelerated towards the Earth, but kind of with a different direction. So this results in a relative acceleration between the interferometers. So still in this experiment, so the experiment we did is very similar in a sense, but this early experiment, the quantum systems were very small. So basically they behaved just like any classical test particle would. They were small, and the interferometer still stayed in the local region. Okay. So the goal of our experiment is just to make the interferometer bigger. So we want to study what happens if we make our atom interferometer bigger and bigger and bigger, and we want to see whether we can observe an acceleration between the two arms. So we have to make it big enough that the two arms of the interferometer follow different trajectories. This is kind of the idea. This kind of experiment was proposed already a long time ago, soon after the neutron interferometer experiment. Aneden proposed that it would be an interesting thing to do to measure this curvature effect in interferometry, and a little later, Aldrich and Matzlin basically proposed the exact experiment we did later on in 1994, where you would have an atom interferometer and some lead blocks you would bring close to the atoms and to see the effect on the atoms. What kind of started this the interest in this kind of experiment for me was basically talking to somebody at a conference who told me, oh, this would be really interesting thing to do. And if you look at the literature, kind of already a long time ago, people were very excited about it. So as you can see here, there's a paper from Baudet and Lemarzal, which basically said it would be a great thing to do to measure the curvature effects on a quantum system. And this paper basically gave the inspiration for the title of our paper. So we basically translated this the sentences and took it as our title. Okay. So before we look at the data, just a quick summary of how atom interferometers work. You come in with some atoms, then you have beam splitters made out of light beams. There are two spatially separated interferometer paths, and at the end you recombine them. After recombining, you have two output ports, and the atoms can end up in as a certain fraction between the output ports. And what you can measure, the only thing you can measure in an atom interferometer is the interferometer phase. So the ratio of the populations in the two ports is the measurement of the interferometer phase. And you can predict the interferometer phase with many different theories, but for instance, you can predict it with the midpoint theorem. And the midpoint theorem is basically valid for most of interferometry applications, and it just tells you that the interferometer phase will be given by the positions of the atom paths at the beam splitter interactions. So wherever the atoms have been, basically their trajectory determines the phase shift. So for instance, if you accelerate the laser beams in respect to your atom interferometer, you will get a phase shift that looks like K, which is the wave vector of the lasers, the acceleration you move the lasers with, and the time squared. This is a very typical phase shift. So what is interesting about this, or important to note, what we already saw before, is it doesn't depend on any atomic properties. So it just depends on the wave vector of the light, the acceleration, and time. Okay. So now we will take a look at the experiment we did in the paper that is described in the paper. So we have two atom interferometers, one very close by, the lead bricks, and one further away. And the idea is to bring the lead bricks just close to the one interferometer, and especially to a certain position where the differential acceleration between the two interferometer parts will be maximum. So on this plot here in the middle, you can see the separation between the two interferometer parts of the upper interferometer is just around 10 centimeters. And if you look at the accelerations from the lead bricks, you will see that the acceleration is on the order of nano g different for the two interferometer arms. So this is the kind of acceleration we expect and we try to measure. So what kind of phase shift are you looking for if you want to see whether the two interferometer arms differentially accelerate towards each other or away from each other as you would expect? So what you would expect is this phase shift here on the left. It's basically the same as a kgt squared phase shift. However, it's not a constant acceleration, but you couple to the differential, also to the difference in accelerations towards the lead bricks, which is given by the gravity gradient, TCC. And this has units of differential accelerations per meter. So this number multiplied by the separation of the two interferometer arms gives you an acceleration. The separation of the interferometer arms is given by the recoil velocity from the interferometer photons, or from the laser photons, over the mass times the time. So this recoil velocity times the gradient gives you some acceleration that is measured by the interferometer with t squared and the wave vector again. So in total, this phase shift is depending on the squared of the k vector. So basically what you need to do is you just make your interferometer bigger and bigger, but you're not only making it bigger and bigger, but you're also making it more sensitive and more sensitive. that's why there is a k-squared scaling. So this is the phase shift we were looking for. And on the left, you can see our data plot where we plotted the phase shift depending on whether the bricks were there or not. So it's a differential measurement between the lead bricks being there and being not there. As you can see, it follows this quadratic trajectory. So the goal with this experiment was to resolve this phase shift well enough so you can distinguish the measured phase shift from the acceleration you would expect if you would have a classical particle traveling along the lower arm and the upper arm of the interferometer. And as you can see, we can resolve the difference between the upper and lower arm decently. So what the atom interferometer measures is no longer the acceleration along one arm or the other, but the average. So it measures the average along the lower and the upper arm. And then the important thing is that those two are no longer propagating along the same trajectory, but really are bent or distorted by gravity. So why do we call this, why do we say that gravity stretches the quantum state? What happens not only is that there is this quadratic phase shift dependence overall on average, so if you sum over over all atoms, but what also happens is that due to these differential accelerations between the arms, the two clouds will no longer overlap at the end of the interferometer, but they will be displaced in space and momentum a little bit. And what that creates is a certain fringe across the cloud, which we measured in a subsequent paper. But basically, the important message is gravity not only creates this quadratic phase shift, but also creates a phase shift across the cloud, simply due to the fact that it's no longer, that the interferometer is no longer closing, but deformed. An interesting coincidence kind of that this midpoint theorem that I mentioned before relies on the Ehrenfest theorem. So the midpoint theorem basically states that in low order potentials, basically for wave packets, for interferometer separations which are small, the phase shift is easily calculated by the positions of the interferometer paths at the laser interaction. It behaves very classically or semi-classically. So the final measurement is made up of these classical quantities, k times x. K, the wave vector, and x, the positions at the laser interaction. Why do we call these classical quantities? So if you would take a classical particle and shine a laser at it, for instance, a mirror, and measure the phase of the laser lines that bounces off, it will have exactly the same shape. So k times x is would be just the phase of the laser that bounces off the mirror. So you can measure these quantities with a classical object. And kind of why is our experiment kind of a little bit beyond that is that the interferometer measures it along two arms at the same time. So we did this experiment in 2016, and as you can see on the plot, there is a solid black line and the dashed gray line. So the dashed gray line is the phase shift predicted by the midpoint theorem, and the black line is the full phase shift calculations. So basically, there is something that is not. There's a small effect that is not basically described by these classical quantities. And we were discussing this quite a bit, how to think about this, this deviation, and also how to make this deviation larger and to study this, this regime a little bit more. basically what we're working on at the very moment. And the way I like to categorize this kind of phase shifts that go beyond the midpoint is that they are quantum. These phase shifts do no longer measure something that you could measure with a classical. And so a famous example of this kind of quantum phase shift is an Aharonov-Bohm phase shift, where you would say that the classical particle has no idea or measures nothing, whereas the quantum particle can measure a flux. Yeah, but this is a very specific example. In the general case, what happens is that the quantum systems no longer measure the phase shift of the quantum system is no longer given solely by the trajectory, but what also comes in are terms that look like energy shifts. So in the case for gravitational interaction, an energy shift is proportional to the mass of the atom. So that energy shifts make phase shift sounds extremely trivial, especially if you think about electromagnetic interactions, right? So what is quantum? It's in the case of electromagnetic interactions, that's a classical example. You shift some two-level system, you make an energy shift or some perturbation, and you will get a phase shift. So sounds very trivial with electromagnetics, but with gravity, it's a lot harder to observe this kind of effects. And this is basically the goal of our current experiments, to try to figure out whether gravity imprints this kind of quantum phase shift. Okay, so what is the long-term future? The obvious, well, not obvious, but for these quantum phase shifts, one of the interacting particles is in a quantum superposition. So in our case, it's the atoms being in a large superpositions, and the source mass is just a classical source mass. So what you could do in the future, which has received quite some interest recently, is the question whether you can observe gravitational entanglement, which basically means that both the source mass and the test mass are in quantum superpositions and they're interacting. This is basically the big question for the future, whether gravity transmits entanglement, basically. Okay, so just a quick look at what kind of experimental tools, or how does the experiment look like in order to do this very simple experiments. So it's very hard to make an experiment simple. So in the case of atoms, what do you need? First of all, you need to make your atoms very cold so that they don't move around too much due to thermal motion. This is one thing. Then the other thing is what you need very high power lasers, just to ensure you can make coherent interactions and don't lose any information to non-coherent interactions. And in our case, what we also have is, or what we need is a long drift time. So in our lab, we have this amazing 10-meter tower where we can achieve free-fall drift times of 2.6 seconds. So this is really very helpful to make good or to make big quantum states and read them out with good precision. So here another look at our authors. Back in 2016, we were all together in Stanford at that time. Most of us are still, but Tim and Daniel are along. Thanks a lot to them, of course. It was a great paper, and especially it was a lot of fun to do the experiment, since it involved moving around 70 kilos of lead bricks close to the tube and back again. So this was quite the workout, but yeah, it was a lot of fun. Thank you.
Okay, thank you for the nice talk. Thanks very much. Yeah, we can all applaud. There's actually an applaud button. I've just learned this now as a Zoom feature. Yeah, thank you. So we have lots of time for questions. Now let me see how we organize this. So perhaps we can try it in a way that anybody wants to ask a question, they can just unmute and show the video, and then raise their hand, maybe physically. So perhaps let's try that. Anybody any questions? Okay, not for now. Now let me ask a question. So you were showing one diagram where you were showing the interferometer, and in the diagram, the interferometer arms were not closing anymore. Now, should I really think of that directly as an implementation of space-time curvature? Is that really directly space-time curvature, or is this something else? How should I think of that?
I mean, there can be various facts why the interferometer is not closing. So basically, the lesson is that that gravity does it as you would expect it. So it's no surprise there. But yeah, I mean, for experiments, this is a big issue. Basically, that yeah, you have to take care of, because otherwise you lose a lot of sensitivity if you don't recombine them with certain tricks. Yeah, but I mean, it's, yeah, this is the gravitational effect in a nutshell, that the two are not closing anymore. Yeah. But I mean, there are other effects doing similar things. So, yeah, for instance, you can change the interferometer time, which does something very similar. Just you don't wait long enough until they recombine.
Okay, but all right. But the fact that they are not recombining is not directly related to a quantity that you would compute from VR directly, I guess. Probably just wondering how that effect is determined in your experiment. What do you mean? Quantity, how large is the effect?
So I mean, the phase shift across the cloud, I mean, the middle, so the average of the phase is given by this quadratic behavior. But in addition to that, there is the phase across the clouds for different velocities and positions is no longer constant. Mm-hmm. Yeah. This is a typical effect of if something is not closing.
Right.
Yeah, so I mean, it just works as you would expect.
Okay. Do we have other questions?
I mean, it has to be that way, that it's not closing. Otherwise, there wouldn't be any differential acceleration.
Right. Right. Okay.
I have a question, if I may.
Miguel, go on.
Okay. So I have never heard about these atom interferometers, and I'm very curious, actually. So I would like to ask you, do they have to be the atoms in some particular internal state, or how do you recombine the atoms? I don't. Can you comment a bit?
I mean, so this is all done with the same internal state. So it would work with any kind of object. Yeah. So you could do the same thing with a rock. Works. I mean, pretty much the same way. So the internal structure is irrelevant.
Okay. So in particular, could you have like an atom being interfered while at the same time its internal components are evolving, or?
Yeah.
Would it be possible? Okay.
I mean, this is completely standard.
Okay, thanks.
or standard problems, basically. Yeah, so I mean, if they have different internal states or whatever, you can acquire phase in the internal states, which would show up in the interferometer phase.
Mm-hmm.
Yeah, so you can have dephasing from internal states. Yeah, but I mean, from a
I propose you an
perspective,
experiment, but I have to read about the setup.
yeah, so I mean, from the gravity perspective, the internal states are not that interesting. I mean, you can make redshifts experiments. Yeah.
Okay, thanks.
Okay. I have directly another question. So I was thrilled to see that you in the future you want to think about the Bose-Vedral Manitou proposal. It seems to me, I mean, it seems to me something in a way completely different. No, I mean, in that case, you would also have a test mass that's in a superposition of.
Yeah, I mean, it's a natural continuation, I would say, to this experiment, the experiment we're doing now. Yeah.
Yes, but I wonder, do you think it's feasible with something that you could do in your lab in the near future? Like, do you already have an idea how you would do this? Or because it seems just so much different than, you put a very heavy brick as a test mass and then you see the effect on some quantum test particle. Now you also want some quantum somehow test mass. Just wonder if you really think you could do that or how realistic that would be.
Yeah, I mean, I think you should try it from at maybe like 10 years, and if it's going well, then it maybe works in 20 years.
Okay.
No, but I mean, I once told that to somebody, or maybe to many people. It's just this kind of experiment that has a complexity of detecting a gravitational wave, I would say. It's not. I mean, people started doing gravitational waves experiments in the 80s or something, maybe even earlier. But it seems to me like this kind of complexity, or maybe not complexity, but yeah. So I mean, it's very hard, and you're still far away, similar to maybe how it was in the 80s with gravitational waves.
Yeah, it would be really exciting. I mean,
yeah, I mean, it's just something you have to go along and see how it goes. I think not obvious that it will work in 20 years or 15. I mean, 10 seems pretty impossible, but yeah, maybe it is impossible, but maybe not.
Okay, great. Other questions? Here's somebody, Archie.
Yeah.
I think. Yeah.
Hello, Peter. Thanks for the talk.
Yeah.
A question comes to my mind. I work in the University of Birmingham Quantum Hub. Do you think in the future, in gravity sensors, an element other than rubidium will be used?
Sorry, can you repeat that?
Usually in gravitometers, rubidium is the element that is used.
Yeah.
Do you think in the future maybe another element would be used, or is people going to be sticking to that?
It's an interesting question. I mean, from the authors, there are two. Jason and Tim are working with strontium, which sounds very promising. Yeah. Yeah. But rubidium is still pretty good. I mean, the biggest downside of rubidium is that it has a finite second order Zeeman shift. So it's always sensitive to magnetic fields, which, I mean, for measuring time varying things, it's not a big issue. Yeah. So I mean, just as a passive test mass, strontium might be better. Strontium also adds other things that rubidium doesn't. Yeah. Yeah. So maybe strontium will replace rubidium as the workhorse. Not obvious yet, but might be.
Thank you.
Do we have more questions? For curiosity, let me ask this. So this lead block that was gravitating doesn't sound like a very, very massive thing. It's so I was just wondering if a PhD student was walking along in the next room or so, did you see any wigglings? Like, how sensitive was it?
So I mean, the thing is, usually you don't walk so close to a tube.
Mhm.
Usually you are like 1.5 meters away or so.
That's
Yeah,
enough.
you could measure it. So I mean, the biggest issue with persons is that they are very tall. So if you squat down, it's easier to see you.
Mhm.
I mean, that's not. I mean, it depends on the distance mostly. It scales down very fast.
Mhm.
But yeah. No, I mean, works. I think I mean, yeah. I'm pretty sure we can just do that in the lab. Also, telling a person to go there and look whether we can see it.
Okay.
Yeah. I mean, it certainly works if you go close to the tube.
Mm-hmm. Mm-hmm. But does that mean you could use your setup somehow as a metrological device at some point?
No, I mean, there are many proposals. I don't know. I mean, Mark Kasevich, I mean, yeah, I mean, there are people that worked and proposed using this for detection purposes, basically, for border control. Yeah. So I'm not 100% sure how readily implemented that is, or how well it works compared to other things. But I mean, in principle, it's how you would do it, how you would do gravitational imaging, so-called.
Okay. And you said that's used for border control? Wow.
I mean, this is. I mean, people were trying to implement it for border control.
Wow. Amazing.
Or building setups, and I'm the wrong person to ask, obviously, but no, it's obviously useful for these kinds of things.
Mm-hmm. Okay. Good. Do you have more questions? Any other questions? Okay, last chance for a question. If not, then nobody. Okay. So then let's perhaps close the session now. So let me thank again Peter for the nice talk. Let me congratulate again our prize winners. So as I said, you will all get this certificate here by mail. Yeah, and it was nice to have so many people attend and join us here. So there will be announcements on Ikoki Vienna's channels on Facebook, on our website. You can watch the talk again if you like on our YouTube channel. So please zoom in there, and if you want to comment, send us comments. It will be also an opportunity to ask other questions that you may not want to perhaps post today. Perhaps you want to read up something first. So yeah, this is a way to connect with us. Yeah, thank you all for coming. And as I said, it would be nice to have some snacks and drinks together now, so we cannot do that. So I'm just here now to wish you a good evening. I hope to see some of you in person soon. Okay, thank you all very much, and good night from Vienna. Bye.
Yeah, thanks for organizing, by the way. I haven't said that right. Thank you.
Thank you.